here is, if all these excited atoms we force to emit photons along the axis of the discharge tube, then you will have an extremely powerful beam of light coming out of this device. The device now cannot be regarded as a viewing source anymore, because light from it now does not travel in all possible directions. However, this unique beam of light will have many fantastic properties that can be put to numerous applications in our day-to-day life. Einstein first spoke of stimulated emission in 1917, but it took more than 4 decades for the first man-made laser to come into being. The first laser, a ruby laser, was operated by an American physicist called Theodore Mayman in 1960 at the Hughes Aircraft Laboratory located in the state of California in America. And the first laser flashing its light fired its imagination of scientists across the world to put it into our day-to-day life in one way or another. And no wonder laser is often nicknamed as solution in search of problems. But before I tell you the realization of stimulated emission in an experimental system, let me very quickly take you through the spontaneous and stimulated emission processes. Let's begin with spontaneous emission. A photon shines on an atom which is in its electronic ground state. And if the photon has just right amount of energy, you know from Bohr's theory that it can actually electronically excite the atom for a while. And the atom, after spending a finite amount of time in this excited state, will eventually come down to the ground state, releasing this excitation as a photon. As these emissions are random in nature, therefore the photon can be emitted anywhere within 4 pi solid angle around this atom. Such an emission is called random or spontaneous emission. Let's see how the stimulated emission takes place. We have now a photon that we call photon 1, which once again electronically excites the atom as before for a while. And when the atom is still in state of excitation, a second photon that we call photon 2, which has exactly identical amount of energy as that of photon 1, now interacts with it. And the excited atom instantaneously comes down to the ground state, releasing a third photon that we call photon 3, which is absolutely identical to photon 2, the stimulating photon in all respect. And most importantly, it travels in the same direction as that of photon 2, the stimulating photon. And that is how the directionality is inbuilt in the process of stimulated emission. Such an emission is, of course, known as stimulated force or induced emission. Through this slide, I shall show you as to how stimulated emission can be exploited to amplify light. For this, we consider two situations. In the first case, let us assume that in our system, the excited state has less population than the ground energy state. And this is the kind of system that we normally encounter in nature. And we shine this medium by beam of light that comprises a bunch of identical resonating photons. By resonating photon, I mean that the photon's energy matches exactly the energy difference between these two energy levels. Now, as this resonating photons travels to this medium, you know from Bohr's theory that the medium will absorb a significant number of photons from this incident group of photon, and what will emerge through this medium will be an attenuated output beam. Thus, the medium behaves here like an absorber, quite expectedly. In the second example, let us assume that we have somehow prepared our system initially with now the excited energy state having more population than the ground energy state. And you once again shine this medium by the same beam of light comprising of that bunch of identical resonating photons. Now, as this photons travels to this medium, you know now from the definition of stimulated emission that the medium now would add more and more identical photons to this incident group of photons by virtue of stimulated emission, and therefore would give out an amplified beam of light. Therefore, you see, the amplification of light is possible if and only if the excited energy level has more population than the ground energy level, a condition that is normally termed as population inversion. Therefore, a light amplifier can be pictured in the following manner. You have an inverted medium, that is a medium in which population has been inverted between two energy levels, and you shine this medium by a bunch of coherent photons. Now, as this photons travels through this medium, the medium by virtue of stimulated emission would add more and more identical photons to this incident group of photon, and thus in turn would give out amplified coherent light. Now you would appreciate that higher is the population inversion, more would be the amplification. Or in other words, we can say that the gain of this optical amplifier increases with increasing population inversion. Now see, a laser is an acronym for light amplification by stimulated emission of radiation. Therefore, a laser also gives out amplified light. But surely it does not require an input coherent source for its operation. If it did, then the laser would have lost almost all its significance. So how does it work then? It amplifies light, and yet it does not require an input source for its operation. Well, to understand that, we must first know what is a cavity. You see, a very simple cavity is formed when two very high reflectivity mirrors are placed parallel to each other at a given separation. Let us consider a typical cavity for which both the mirrors have 95% reflectivity. And let us shine this cavity with a beam of light of power 1 watt. Now, of this 1 watt, the front mirror is going to reflect 95% back. Therefore, only 5% of this 1 watt, that is 50 milliwatt, is what would get inside the cavity. And of this 50 milliwatt, the rear mirror is going to reflect 95% back. Therefore, you yourself can calculate and say the cavity would hardly transmit anything of this incident light to its other side. Fortunately, this is not always true, else the cavity would have lost all its significance in the context of a laser. A very simple experiment would make the cavity reveal its deepest secret. For this, we derive this input beam of light from a tunable source. You see, tunable source is one that gives out light of continuously changing wavelength. And in order to monitor the transmission of the cavity as a function of the wavelength of this incident light, we place a detector on the other side of the cavity and monitor its transmission. The result of this experiment has been captured in this picture. We'll see that for most of the wavelengths, quite expectedly, the cavity hardly transmits anything, almost 0 watt output. But what is intriguing is that at certain discrete wavelengths, the cavity transmits almost everything that is incident on it, the entire 1 watt. For these discrete wavelengths, the cavity is said to be on resonance. Thus, you see that a resonant cavity is one that transmits everything that shines onto it, and a non-resonant cavity is one that reflects everything that is incident on it. On closer examination, you would see that those wavelengths, half of which times an integer fits exactly inside the cavity, are actually resonant to the cavity. Therefore, mathematically, the resonant equation can be written as n into lambda by 2 equal to L, where n is an integer, lambda is the wavelength, and L is the length of the cavity. And in terms of frequency, the same equation can be rewritten as nu n equal to nc by 12, where c is the velocity of light. These discrete frequencies, which can oscillate back and forth inside the cavity without decaying, are called cavity modes. And the spacing between two adjacent cavity modes, which is called free spectral range of the cavity, can be readily calculated from this equation and be shown as inversely proportional to the length of the cavity. An obvious analogy is Bohr's orbits of electron. You know that the electrons can oscillate without decaying only in those orbits into which its de Broglie wavelength fits an integer number of times. You may still be wondering, so what? Even if there is a resonance, the front mirror is still going to reflect 95% of whatever is incident on it. How come therefore everything gets to the other side in the first place? Well, to understand this, we must refer to this slide. You see, initially, the intracavity photon flux, that is the density of photons present inside the cavity, is 0. Now we shine this cavity by a beam of light at a continuous beam of light at a resonating wavelength. Now the tiny fraction of light that gets inside the cavity would actually oscillate back and forth inside the cavity because it is resonant to the cavity, and therefore the intracavity photon flux gradually builds up because the input light is continuous, and it keeps on building up until and unless an equilibrium condition is reached, which in this particular case occurs at a power level of 20 watt, because you see 5% of 20 watt is 1 watt. Therefore, in the equilibrium, the cavity gives out 1 watt as its output. And while the same 1 watt is also incident on the cavity as its input, and the cavity all the while maintains an intracavity power at the level of 20 watt. You might have already figured out as to what role cavity plays in the operation of a laser. You have an active medium, that is a medium in which population has been inverted between two energy levels, is actually placed inside the cavity. And as you know, that an atom or molecule can only spend finite amount of time in an excited energy level. Therefore, the energy levels are actually spread in frequency in accordance with Heisenberg's uncertainty principle. Therefore, the gain that you have created between these two energy levels does not occur at a single frequency. Instead, it is spread over numerous frequencies. Now you see, for all these frequencies, there is gain. Does it mean that the lasing would occur on all these frequencies? The answer is an emphatic no. Lasing would occur only on those frequencies which are cavity modes, which can oscillate back and forth inside the cavity without decaying. All these discrete frequencies shown here are cavity modes, and all these cavity modes have gain. Does it mean that lasing would occur on all these cavity modes? The answer is once again no. To understand this, let us go a bit deeper. You see, in a typical laser, reflectivity of one of the mirror is maintained at 100%, meaning no photon flux can leak through this mirror, while a small transmission loss is provided to the other mirror, allowing the coupling out of the laser beam as an useful loss. If this loss is independent of the frequency, then it can be represented by a straight line parallel to the frequency axis in this gain curve. Lasing would occur only on those cavity modes which have net gain, meaning whose gain actually exceeds loss. In this particular example, you can see there are 1, 2, 3, 4, 5 such modes for which gain exceeds loss, and therefore lasing would be affected on all these 5 modes, and the emission feature of the laser would look somewhat like this. The mode with higher gain also will have higher power, but not very monochromatic. You may begin to wonder. True. In order to make the emission more monochromatic, the emission width of the laser has to be reduced. This can be achieved in one of the following two ways. First, the broadening of the gain can be reduced so much so that now only one mode, in this case the central mode, has gain which is more than the loss, and therefore lasing will be affected now only on this central mode. So it will be basically a single mode laser, and the emission of the laser will now be highly monochromatic. The same also can be achieved simply by reducing the length of the cavity, as then the cavity modes are pushed away from each other, therefore once again providing the condition for which only one mode, in this case this mode, has gain above loss and therefore would be able to lase. However, monochromaticity in both these techniques have been attained at the expense of the efficiency or the performance of the laser. The same also can be achieved simply by placing a dispersive element such as a prism inside the cavity. You see, the prism actually basically splits the cavity mode spatially, thereby allowing at a time only one of the cavity mode to fall normally on the output mirror. And therefore, this mode alone would be able to oscillate back and forth inside the cavity and would be able to extract energy from this active medium, which is continuously being pumped towards maintaining population inversion. All other modes which fall obliquely on this mirror would simply get lost and would not get a chance to laze at all. Therefore, as you can see, the monochromaticity in this case is attained at no expense of the efficiency of the laser. And further, by giving a angular tilt to this mirror, different mode can be brought to lasing, thus providing a way to tune the wavelength of the laser. Thus, you see that combining uh, cavity with the population inversion has not only given lasers its directionality, but also has made its emission more monochromatic. Incidentally, however, the first laser that Meyman operated in 1960 did not make use of any cavity in a true sense. You may be wondering as to what trick that Meyman played that allowed him complete dispensation of a cavity. Well, let us digress here a little to tell you the story that goes behind the first experimental demonstration of amplification of light by stimulated emission of radiation. The paper that Meyman wrote to report the first operation of a laser comprises few illustrations and a very small text. It seemed that Meyman did the experiment in the morning, wrote the paper in the afternoon, and dashed it off to the editorial office of Physical Review later before the end of the day. Such an urgency stemmed from the fact that at that point of time, many laboratories in the world were working hard towards achieving amplification of light by stimulated emission of radiation. The editor of Physical Regulator, however, was not impressed. He felt the data presented by Meyman in his paper was too scanty to warrant publication in a journal of the repute of Physical Regulator. He therefore took a unilateral decision and rejected the paper, a decision for which he has to repent very soon. The paper then crossed Atlantic and soon reached the editorial office of Nature. The editor here behaved behaved more wisely and got the paper published promptly. That has since been regarded as the first report on the amplification of light by stimulated emission of radiation. It was not long before the editor of Physical Regulator apologized to Meyman by writing him a letter to that effect. Well, returning back to science, let us see as to what was the signature in Meyman's experiment that convinced him to believe that indeed he has operated the first ever laser. You see, the experimental system used by Meyman was extremely simple. He used a cylindrical ruby rod and optically pumped it by deriving light from a conventional traditional flash lamp. And he basically, and the ruby would then fluoresce light at a correspondingly longer wavelength. And the fluorescence will have a spectral weight for the same reason for which, as we saw, gain has a spectral broadening, the Heisenberg's uncertainty principle. Meyman basically wanted to study three cases. Study the fluorescence as a function of wavelength in three cases. In the first case, he pumped his ruby very softly, very softly, and the spectral width of the fluorescence matched the known fluorescence width of ruby absolutely fine. In the second case, he increased his intensity of pumping, but still not high enough to create population inversion along the length of the ruby. In this case, although the fluorescence exhibited a rise in intensity in accordance with increased intensity of pumping, but the spectral width of the fluorescence was invariant. It was just same as before. In the third case, Meyman pumped his ruby very hard, so hard that it created population inversion along the length of the ruby. And in this case, Meyman found there was a significant narrowing of the spectral width of the fluorescence. Now, as the probability of stimulated emission at a given frequency increases with increasing number of presence of photon on that frequency, Meyman knew for sure that the spectral narrowing of the fluorescence is indeed a signature of amplification of light by stimulated emission of radiation. I hope I have made it amply clear to you as to why Mayman is still regarded as the inventor of laser, even though he never operated a laser based on the concept of a cavity in the true sense. Now we see the integration of cavity with stimulated emission has given laser almost all its attributes like monochromaticity, coherence, tunability, directionality, brightness. A laser can also be operated both in continuous and pulsed mode. In the pulsed operation, the laser's output power can be greatly enhanced, although the average power may still remain the same as in case of continuous operation. By judicious manipulation of some of the operating parameters of the laser, it can be made to emit a giant pulse into which huge amount of energy would be confined within a short time, thereby producing enormously high intensity that can simply do wonder. By manipulation of some other operating parameters of the laser, it can be made to emit ultra-short pulses that can go down even to the regime of femtoseconds. All these, however, beyond the scope of this presentation. But all these unique features of lasers have resulted in wide application in diverse areas like medicine, manufacturing, nuclear industry, communication, defense, science and education, conservation of artwork, entertainment, energy, holography, almost anything that you can think of. You name any discipline, a laser has almost invariably made a cut into it. Now, owing to time restriction, it won't be possible for me to present here all the applications that laser has. And I must also confess at this point that I myself am not aware all the applications that laser actually have, nor am competent enough to tell you all about it. I have therefore decided to present here just a glimpse of only some of the applications that I thought would be of your interest. Let us begin from lasers in medicine. You see, lasers in medicine has been almost as old as the laser itself. For in early 60s, an intense pulse from a ruby laser, the laser that was the first to be developed, was used to treat retinal tear, which is a kind of eye disorder where the retina gets detached from the layer underneath. And before the advent of laser, a person with such a problem in his or her eye would almost invariably the vision to that eye, as it would have been impossible for an eye surgeon to work on the ultrasensitive membrane, that's what retina is, with his conventional tool. And now, with laser, the cure is not only total, but it also occurs almost instantaneously. It just needs an intense pulse to be shown onto the eye lens. And eye lens then this focuses the beam of that light into the disjointed region of the retina. And huge amount of energy delivered within a short time basically fuses the detached retina to the underlying tissue. This method of treatment, as you would appreciate, is often referred to as eye welding. In case of surgery with laser, a surgeon uses laser as a knife of photons, which can work simultaneously as a cutting and coagulation tool. You see, laser can easily cut through human tissues because the heat deposited by it can readily vaporize its water content, and the deposited heat also simultaneously causes filling of the opening made by the laser. Therefore, when a surgeon uses laser as a knife of light, he or she can easily make incision on patient's body without, however, even a drop of blood being oozed out. Such bloodless surgery assumes more significance in case of operation involving more vascular region of human body. If a conventional method of operation is performed here, then the patient may even die due to excessive bleeding, even though the surgeon might have accomplished his task quite satisfactorily. In the treatment of cancer, laser reaching the tumors either directly or through optical fiber can heat up the cancerous cells so enormously that it can simply damage or even destroy them. Laser also has the capability of an early diagnosis of malignancy. For this, the suspected region of human body is first exposed to the laser beam, And the study of subsequent fluorescence actually helped diagnosing malignancy at a very, very early stage. At this point, let me uh, uh, make a note of the fact that laser-assisted targeted drug delivery is a very topical area of research, and it is believed that one day treating cancer with chemotherapy will be a much more efficient method of treatment with greatly reduced side effects. You see, laser has the capability to manipulate motion of microscopic objects through a tweezer-like fashion. And as some of you may be aware, that Professor Ashkin was awarded Nobel Prize in Physics only a couple of years ago for his pioneering work in the area of optical tweezers. The idea here is to use laser to guide and eventually direct the injected micro drug particulates onto the malignant cell alone. And as I said, one day treating cancer with chemotherapy may be a much more efficient process of treatment. In laser angioplasty, laser has the capability to remove coronary blockage that basically is deposition of fat in the coronary artery. And laser of an appropriate wavelength and intensity can actually remove such blockage through a mechanism that is called laser ablation. Without going into detail, let me mention here that for carrying out laser angioplasty, a patient is not even required to be admitted in hospital. He or she can simply be treated as an outpatient. Before moving on to another application of laser, let me very quickly take you through use of laser in cosmetic surgery. The area that stands out here is laser skin resurfacing, which basically involves removal of facial wrinkles, scars, and blemishes. That the appearance of wrinkle can greatly devastate the look of one's beautiful face has been illustrated in this slide, where the same lady has been photographed over passage of time. At this point, I run a video to basically where time basically runs in the reverse direction. And as you watch through this video, you would wonder if indeed time can be made to run in the reverse direction, making this video a reality. Now we all know that time cannot be reversed. So if time cannot be reversed, why not the skin? And that's what laser does precisely in this application. Extended ultra short concentrated pulsating beams of light flashes on the irregular skin of the human body from where wrinkle is to be removed. This can remove the unwanted damaged skin in a very precise manner, just one layer at a time. And this one layer at a time is what does the trick here. And usage of extremely ultra short pulses actually allows to make it happen. You see, the duration of pulse is so short that the deposited heat cannot penetrate into the bulk within the duration of the pulse, and instead it stays localized on the topmost layer of the skin, allowing its ablation and layer by layer. And as the treated area heals, the new skin that forms is both smoother and firmer. Laser skin whitening, which is another variant of the laser skin resurfacing that uses short bursts of laser light to lighten skin and remove dark blemishes. By reducing the number of these melanocytes, the skin's natural pigment production process can be slowed or even stopped, causing the skin to whiten gradually. No wonder laser skin resurfacing has gained a lot of popularity in the West towards arresting one's aging effect. In India too, many celebrities and wealthy individuals are believed to have used laser to preserve their youth by way of removal of facial scars, wrinkles, and blemishes. Another area where laser in cosmetic surgery has gained popularity is use of laser as a hair remover. Most of the important features of laser as a hair remover I have uh, summarized here. First and foremost, it is a permanent procedure, meaning you have to do it only once in your lifetime. And having hair free for life is an absolute, uh, an incredible experience would be to many. It is of course a precise technique and therefore can be applied on any part of human body wherever one wants. It is indeed cost effective when compared to lifetime spending on known ways of removal of hair. It is a very easy and painless process. Let us go a bit deeper and see as to how does laser remove hair from the human body in the first place. A concentrated beam of light is first aimed at the location of human body from where hair is to be removed. The wavelength of the laser used is such that while hair absorbs it, the skin does not. And the absorbed heat rapidly burns the hair, reaching the root of the hair and thereby damaging the follicle that basically is the cavity that contains the root of the hair so extensively that that in turn retards any future growth of the hair. Skin remains practically unaffected because it does not absorb any energy from the incident laser beam while all the hairs are gone. Very attractive for sensitive skin and that cannot otherwise bear the burn of conventional methods like shaving, waxing, etc. Let me very quickly take you through use of laser in fashion industry. Many of you might have wondered at one time or another if the intricate, elegant, classic pattern ornamented on your grandma's doily can be transferred onto your clothing itself. And indeed, the incredible beam of light that the laser gives out has actually made it happen. Laser cut design, as a matter of fact, has now revolutionized the fashion industry. The important advantages of laser cut design have summarized here. Extra accuracy, clean cut, and seal fabric edges are the salient features that make this technique stands out among the rest. And the extremely small divergence of the laser beam actually makes this possible. You see the typical divergence, that is the angle through which the laser spreads as it travels through space, even for a commercially available laser, can be incredibly small, lying in the range of just about a milliradian, which is just a small fraction of even a degree. When the beam emitted from such a laser is focused by a lens of focal length, say 10 centimeter, then the diameter at the focal plane would be just about 0.1 millimeter. That is less than even the average width of a human hair. The area of the fabric with which the laser interacts thus is vanishingly small. This in turn gives very clean and precise cut with extreme accuracy. This is one method that is applicable to multiple materials, for example, silk, nylon, leather, neoprene, cotton, almost anything that you can think of. Cuts are made without the need of applying any pressure on the fabric, so no intended mark and hence no post-operative treatment. Easy integration with computer makes it versatile and cost-effective and less likely to be copied unless you have the exact software to create an identical pattern. Now at this point, I would like to run a video to basically demonstrate to you the kind of ease, swiftness, and accuracy with which a laser cut design product can be manufactured. A 500 watt continuously working carbon dioxide laser has been used for this application. And as you watch through this video, you see for yourself with the kind of use, swiftness and accuracy with which, in this case, a denim jeans can be manufactured. Only a little bit of stitching left and the jeans is ready to be worn. No wonder that today use of laser in fashion shows and by celebrities all across the world have practically crossed the limit of counting. In laser rangefinder, laser measures distance to an object and most of the conventional kind of laser rangefinder works on the principle of time of flight technique where a short pulse of the laser is first aimed towards the object and the time taken by this pulse to return back to the sender is what is actually measured. Usage of a retroreflector ensures that the return beam travels in a direction exactly opposite to the incident beam. Therefore, the required distance would simply be half of the travel time of this pulse multiplied with the velocity of light. Perhaps many of you are not aware that in early 70s, when NASA had undertaken the famous lunar mission, then during one of the trip to the moon, an American astronaut called David Scott had actually placed a huge metal reflector on the surface of the moon, precisely on July 31, 1971. This is the picture showing Mr. Scott placing a retroreflector on the surface of the moon in a manner so as to be easily accessed from Earth, also clearly seen in this lunar shot. Subsequently, a highly directional green helium neon laser beam was aimed from the ground station to the moon, to the mirror placed on the moon. And measurement of the to and fro journey time of the laser pulse from the Earth to moon and back to Earth again allowed estimation of distance between Earth and Moon to an incredible accuracy of 2 centimeters, which is equivalent to an error which is less than even 1 part in 20 billion. In this particular uh, photograph, Moon has been deliberately overexposed to ensure that the trajectory of the helium neon beam is also clearly seen. Now, I would like to uh, invite your attention to the contrasting black sky in this lunar shot. You see, the black sky basically provides signature of absence of any atmosphere in the lunar sky. And as there is no atmosphere, therefore, there cannot be any scattering of sunlight in the lunar atmosphere. And that is why lunar sky appears absolutely black. And as we know, it is the Rayleigh scattering of the sunlight in our Earth's atmosphere that makes our sky appear blue. LIDAR, which is the acronym for light detection and ranging, which can measure distance between two objects, that works on this principle and runs on laser, are now commercially available. And as a matter of fact, you can place order for a handy LIDAR with Amazon if you so wish. Laser-based ranging system is the key to safe navigation in driverless vehicle, and the market for such vehicle has been projected to exceed even $500 billion by 2026. A selfless, a driverless car is a vehicle that is capable of sensing its environment and moving safely with little or no human input. Although a model where you can drive while sleeping, reading, or tweeting is not available at the present time, but there are some high-end cars available today with advanced feature of switching over to laser eye while driving in the highway on a gloomy and rainy night. This facilitates negotiating with the glare of the headlight of an oncoming vehicle coming from the opposite direction, or averting collision with an object approaching from a perpendicular low road not directly visible to the human eye. Through this slide, I shall show you as to how the advent of laser has greatly reduced the difficulty of setting up of an optics-based experiment in the laboratory. Let us consider the case of Michelson-Morley experiment. This is the schematic of Michelson-Morley experiment. The beam of light from the source, after it's passed through an aperture, is made to shine on a beam splitter. The beam splitter then splits the beam into two parts. One part travels through a moving mirror, the other part moves towards a fixed mirror. And the two return beams are then made to interfere on a screen. Now, formation of contrasting fringe would be possible if and only if the following two conditions are met. First, the length of the two arms of this interferometer must be as nearly equal as possible. This basically relates to temporal coherence of this source. And then the source should be apertured down as much as possible to make it spatially coherent as well. A source is often characterized by a parameter called coherence length, which is basically measure of the monochromaticity of the source. Higher is the monochromaticity, more is the coherence length, and vice versa. Without going into detail, let me tell you that that for uh, for a contrasting for formation of contrasting fringes, the difference of length of the two arms of this interferometer must lie within one coherence length of the source. Now, for a sodium vapor lamp, which has traditionally been used as a source of light in optics-based experiment in the laboratory, the coherence length of such a source is just about a centimeter, and 1 centimeter being too small a length. Often, as you know, an optical compensator is used in one of the arms of this interferometer, and the rotation of which basically optimizes the visibility of the fringe on the screen. Now, even a commercial helium neon laser has a coherence length which is tens of centimeter. Therefore, even if a commercial helium neon laser will replace this sodium light, the Michelson-Morley experiment can be uh, done with so much ease, because now you don't need any optical compensator, tens of centimeter being too long a length. For a very highly stabilized helium neon laser, the coherence length can be as high as 100 kilometer. That gives rise to the prospect of setting up this Michelson-Morley experiment, even when the lengths of the two arms differ by more than tens of kilometers. This thus gives rise to the prospect of gaining an advance warning of an impending earthquake, flood, or volcanic eruption. For this, while you can be at the comfort of being inside the laboratory, the moving mirror can be fixed on the base of a volcano. As long as the volcano is calm, this mirror would be steady, and so would be the path difference of these two arms of the interferometer, and so would be the fringe pattern. It would be rock steady. Now, even a very tiny level of seismic disturbance that invariably precedes a fully blown volcanic eruption can impart a tiny movement on this mirror, which then gets basically translated as shift of the fringe in the screen, thereby serving an advance warning of an impending volcanic eruption. I must also note here that now there exists a variety of uh, interferometers that run on this principle, that works on this principle and runs on laser. They're now commercially available and can be employed for a number of scientific research and educational aids. Through this slide, I shall show you as to how the advent of laser has opened up a new branch of optics that is called nonlinear optics. You see, today we have laser that gives out coherent light that spans over infrared, visible, ultraviolet, and even vacuum ultraviolet region of electromagnetic spectrum. But laser usually gives out coherent light at discrete wavelengths with lots of gaps in between. Nonlinear optics help populate these gaps by way of converting coherent light at one wavelength into coherent light at another wavelength. Let's see, how does it happen? You see, extremely high intensity associated with the laser beam can exploit nonlinear dependence of polarization and field to combine in certain special crystals two photons into one, or split one photon into two. The phenomena of birefringence associated with these special crystals ensures same refractive index for both these waves inside the crystal. Therefore, both the waves can travel through the crystal at the same velocity, thereby allowing continuous exchange of energy from one wave to the other. This is actually an actual experimental setup showing the conversion of red light into blue light through such nonlinear optical conversion process. As you can see, two red light photons of frequency omega shining on a suitably oriented crystal get converted into a single photon of frequency 2 omega, thereby converting red light into blue light. Laser assisted surface cleaning. It seems almost like a fundamental law of nature that surface becomes dirty. You clean your eyeglasses, dust your household items, take extreme care on the laser resonator mirrors or other delicate objects in your laboratory. But it's only a matter of time before dust settles again. In case of semiconductor industry, usage of even very expensive clean room technology cannot altogether rule out the possibility of contamination of integrated circuits during the production. And as the microstructure grows smaller, the problem of contamination becomes even more severe. The antique paintings and the ancient art objects kept in the national museums all over the world lose their brilliance over time, primarily due to the presence of dust and moisture. Example of dust invasion in the world we live in are plenty. The major concern here is that most of the conventional methods of surface cleaning, such as mechanical or chemical methods, are almost always abrasive in nature and therefore can easily leave their signature on the surface being cleaned. We cannot, of course, run the risk of losing the antique value of the ancient art objects, or for that matter, having the surface of ices etched. In case of nuclear industry, the problem further multiplies as the contamination here is of radioactive in nature, and so comes the possibility of exposure to the personnel. Understandably, therefore, the researchers have eventually turned towards laser, and indeed, laser has helped solve most of the major issues pertaining to surface cleaning in a remarkable manner. But how does the laser clean a contaminated surface in the first place? Well, this is a very simplified, oversimplified picture showing just a small cross section of the substrate and a single contaminant particulate sitting atop and is linked to the substrate by means of some kind of short range van der Waals bonding force. And as the laser beam shines onto it, two things can happen. First, the particulate itself can absorb energy from the incident laser beam. And if the laser is a pulse laser and can deliver large amount of energy within a short time, and that's what laser does in this application, then the particulate, after absorption of large amount of energy within a short time, becomes instantaneously very hot and rapidly expands in all directions except to the direction to which it is attached to the substrate. And as it cannot expand in the direction of the substrate, it instead exerts a force onto the substrate. The substrate, being a rigid body, returns this force as a reaction force, almost undiminished, onto the particulate. If this reaction force exceeds the van der Waals bonding force, it will result in expulsion of the particulate from the substrate surface. As the laser beam shines onto the substrate, the second thing that can happen is the substrate also absorbs energy from the incident laser beam, becomes instantaneously very hot and rapidly expands in the upward direction, thereby pushing the particulate up. If this upward push exceeds the van der Waals bonding force, it once again results in dislodging of the particulate from the substrate surface. However, in the actual practice, the contribution towards generations of such clearing force can come from the absorption of laser beam by both the particulate as well as the substrate. But the important point that needs to be noted here is that by controlling the parameters of the laser, it can be made to just softly caress the substrate surface, just remove the contamination, and in no way alter the property of the substrate surface underneath. And therefore, if a laser is used to clean a substrate, the virginity of the substrate will be maintained. Virginity of the surface will be maintained. And that is why laser has gained a lot of popularity as a cleaning source for antique objects, because the antique value of the object will not be compromised with if a laser is used to clean such objects. And that is why laser is now being increasingly used in many countries, in particular Italy, that you know has a very rich collection of antique objects. Laser in defense. So whenever we think of military application of laser, the first thing that crosses our mind is strategic defense initiative. You see, during the Cold War, when Ronald Reagan was America's president, America made an ambitious plan to shield its territory by placing very powerful lasers at strategically located orbits with the capability of striking any nuclear warhead that would have been fired from Russian or any other enemy country's soil. The idea was to destroy the warhead in the sky of the country of origin itself. After some initial test experiments with mixed success, this scheme was eventually shelved owing to the cessation of Cold War in early 90s. Now, as far as military application of laser is concerned, it can serve in both ways, as a guide as well as a weapon. The best example of use of laser as a guide is laser-guided missile. The principle of operation of a laser-guided missile has been schematically illustrated here. An infrared laser carried by an army aircraft shines onto the target which is stationary at ground. Missile, when released from a second aircraft, can actually track the ray of light which is being scattered from this target which is stationary at ground, and therefore the missile will hit the target without fail. Precision strike. Such laser-guided bombs were first used by America in Vietnam War, however, with mixed success. The technology of this laser-guided missile was, however, perfected during the Gulf War. These laser-guided bombs with the capability of precision strike made possible for the United States of America to critically weaken the fourth largest army of the world at that time, namely the Iraqi army, while suffering only light casualties themselves during the days of the war. Laser, as I said, can also be used as a weapon to destroy very fast-moving objects in the air, which when compared with the speed of light would appear to be almost frozen. For instance, on sighting a very fast-moving missile in the midair, the laser carried by an army aircraft would fire a giant pulse which will contain huge amount of energy within a short time in the direction of the missile. And during the travel time of this laser pulse, which travels at the velocity of light, the missile would appear to be almost frozen and would be instantaneously destroyed. You see, during communication between 2 points, it is always, it is utmost important to maintain the secrecy of message, in particular when the country is at war. In a future talk, when I gave one, I'll show you as to how science of chaos can combine with laser to make communication between 2 points absolutely secure. This, of course, represents another important military application of laser. I think I must stop here. Thank you for your patience and attention. Thank you very much.
Thank you, Dr. Bishwas. Thank you very much. Now the forum is open for questions. Anybody want to ask questions? Youngsters, students? Hello? You can unmute now. All of you can unmute.
Sir, I want to ask one question.
Yes, of course.
Sir, for a skin treatment, a laser is being used. Whether it is having any side effect?
Yes, actually, you say there is some side effect, but there is no major side effect. That's why the agencies of different countries, the federal in America, it is that FDA, what it is called, has allowed usage of laser. Now there are many places where you can have such treatments done. Even in our country, India, such treatments are available. So there is some side effect, but it's not. There is no major side effect, major issues.
Okay, sir. Thank you.
Yeah, I just want to ask one question. LIDAR technology.
Please, who is speaking? Who is speaking this?
My name is B. Gopalan from Hyderabad.
Okay.
From NFC.
Yeah, interesting.
Yeah, this LIDAR technology that has been recently developed, has it come of age, and are we using it in India?
LIDAR. Yes, of course. Leader is now, as I said, that you can also buy a leader for your domestic use.
Oh, okay.
How much it cost? How much it will cost, sir?
I think it will be within $100. If
Oh,
you buy a handy leader,
okay, okay. Good.
I am Gupta from ISRO.
Yeah. Yes,
I would
ask
like to
question.
know, yeah, I would like to know, like our Chandrayaan 2, we lost the mission. Now, what kind of reflecting surface we could have put on the Chandrayaan 2 so that laser could have helped in locating it in the case of disaster what we faced?
what kind of reflector?
Yeah, what kind of reflector or something we should have put on the Chandrayaan 2 in case of this mishap, we could have located by the laser beam.
See, first of all, let me tell you that the distance of moon, which has been calculated, for that a very special kind of retro reflector was required to be put on the surface of the moon, and then a very highly converging, highly directional helium neon laser beam was aimed from the ground station precisely to that mirror which was placed on the moon. Now, because you see, that some component of that after reflection from that mirror should reach back the earth. Now, I would not be able to answer your question that how difficult it would be
Okay,
to
okay.
locate it by laser. Of course, theoretically it is possible, but to implement it practically.
No, just to, hello? No, just to make one more point, if it is possible. 1 minute.
Sorry.
See, suppose we use the laser beam from the ground to locate the Chandrayaan, but the
Yes.
reflected light need not to come to the Earth. Let my moon orbiters can take the signal from there and transmit to back to the Earth. So
Yes.
reflection is not directly come to the Earth. It can go to the moon orbiter satellite.
Maybe for future Chandrayaan mission, uh, this can be thought of.
Right. Okay. Thank you. Thank you.
Sir, I am Sasank. I have a question, sir.
Yes.
Whether laser can be used for very high speed RPM measurement of the order of lakhs of RPM, rotational speed.
Yes. See, laser velocimetry is a very common technique to measure the velocity of any object. So I would guess that it should be possible. It will work in the same principle as on which laser velocimetry works probably.
Rotational speed, sir.
Yes,
Okay.
it should be possible.
Sir, sir, can you explain something on nuclear application, laser application and nuclear?
Yes. In nuclear application, you see laser isotope separation.
Enrichment.
I don't know whether you have heard of it. Separating two isotopes. See, isotopes, because of their different nuclear mass, the energy levels are different. So,
Okay.
if you have a very highly monochromatic laser, you can selectively excite one of the isotopes.
Okay.
And once you have excited one of the isotope, then you can readily ionize that isotope, while the other isotope, which is at the ground state, will remain unaffected. So the one which has been ionized, you can use the magnetic field and electric field to separate the two isotopes. So this is one important nuclear application.
So which type of laser normally it is used, CO2 or helium?
No, it depends on which molecule or which atom you want to target. If it is uranium, then you have to use some visible laser.
Some visible. Another question, another LIGO, that is called laser infra, something on this earthquake or some measurement, seismic measurement. What is the principle in that? Laser interferometry?
Yes, it is some kind of laser interferometry. I won't be able to tell you precisely what it is, but LIGO, as you know, is assumes very significance in the context of this recent experiment based on detection of gravitational waves.
Okay.
So laser decontamination also possible, no?
Yes.
Decontamination using laser.
This is another nuclear application for cleaning radioactive
Yeah.
surfaces. You
Yeah.
know that by controlling the parameters of the laser, you can just remove the contamination from the surface, and that way you can minimize the volume of the secondary waste. And reduction of the volume of secondary waste is has a very important implication in nuclear industry. That's why laser has gained a lot of popularity as a decontamination tool in nuclear industry.
Okay. And the fuel chopping or cutting, which kind of lasers are preferable?
See, it depends on what is the material you are interested. If it is a ceramic material, then you would use carbon dioxide laser. If it is a metallic material, then you would use ND-ARG laser.
Okay. So which is more powerful, CO2 or ND
Both
yttrium?
the lasers can be made very powerful, and
But why ceramic case it is only
because
CO2?
ceramic, you see, they are molecule. So CO2 is an infrared laser. So the
Okay.
molecule will be vibrationally excited. So
Okay.
the energy of the photon is such that it can cause vibrational excitation. While the atom, metal, in atomic form, it will absorb energy from a visible laser the best way. That's why
Oh.
you a visible laser.
So neodymium is a visible one. Neodymium yttrium.
Yes, it is. It is not really visible. It is in the near infrared, but carbon dioxide is in the mid infrared. So carbon dioxide cannot be absorbed by metal.
Okay. Okay. Thank you, sir.
Anybody else want to ask question?
Sir, I am Cherian from Nuclear Power Corporation. I have one question.
Ask.
Uh, Sir, this laser technology can be used for enrichment of uranium also. How it is done?
Yes, actually, there are techniques which makes use of uranium both in metallic form, atomic form, as well as in molecular form. In molecular form, uranium hexafluoride, which is used, for which you need an infrared laser, where carbon dioxide laser may find application. While for if you want to separate uranium isotope in the atomic form, then you need visible laser like copper vapor laser, dye laser.
In this particular case, the uranium will be in gaseous state or like uranium
Gaseous state,
hexafluoride?
of course, gaseous state. You will have to generate uranium vapor, and then the laser must interact with the vapor, laser of appropriate frequency, which can selectively excite one of the isotopes, precisely uranium-235.
Oh.
Okay. Anybody else? One fellow asked one question in the chat box. Question is that Dr. Bishwas,
Yes.
hair removal has got any side effects?
Yes, there are side effects, but the side effects is not of very great significance. So that is why it has gained popularity.
Okay. Then which crystal is made use of? I don't know. Somebody asked one question. What is the crystal made up of?
For this non-linear conversion,
I don't know. He hasn't mentioned
yes,
anything.
These are very
Okay,
special crystal, and depending on the wavelength, the crystal would vary. For infrared, you need one type of crystal. For visible conversion of visible light, you need another type of crystal. But these crystals are generally very expensive.
Can we use a laser in treatment of plant?
Plant.
Somebody
Like,
asked a question. That's a question.
What kind of treatment? I'm not very
I don't know.
sure about what is the treatment he's referring to.
Nothing else mentioned. Anyway, forget. Hey, anybody else want to ask question? Otherwise, we are going to stop it.
Sir, am I audible? I have a question.
Tell me. Ask fast.
How this NDR crystal is made?
What is that? Question is not clear. Say loudly.
NDR crystal. How it is made?
India laser, how it is made?
Crystal.
Dr. Bishwas?
Yes.
What is the question? I could not hear properly. I don't know.
I'm not sure what is the question.
Can you speak loudly, please?
For any reason.
How this NDR crystal is made? How this crystal is made?
How is the crystal is made? Crystal is made.
Yeah, NDR crystal.
He's asking how the crystal is made.
Yeah, the crystal is made. That is a different ball game. We do not make the crystal. We buy them and use them for nonlinear conversion. So this question probably would be best answered by somebody who specializes in crystallography, and but these are actually single crystal, and they're very expensive, and growing such crystal is a very difficult job. It is a very complex process.
Okay.
One more question from Gopalan.
Yes.
Yeah.
So, this LASIK surgery for the eye, is it harmful or is it permanent?
No, it is permanent. You see, before the advent of laser, as I said, a person with such a problem in his or her eye would almost invariably lose vision to that eye, because it would be impossible for an eye surgeon to work on the ultra-sensitive membrane like retina with his conventional eye. Now, for a laser, what it would be, the treatment would be, it's just the total treatment can be just few seconds. The patient will sit and an intense beam of light, the duration of which would be few milliseconds, would be just shown onto the eye lens. And the eye lens would then focus the beam of light onto the retina. And you know, when you actually weld two metal piece, you join them, and at the region of where they're joined, you actually deliver a lot of it, melt them quickly, and rapidly cool them, so they become a single piece. So it is something like that. You have delivered so much energy within a short time, within few milliseconds, that the thing will melt and it will rapidly cool and get joined into one. So it is just that pulse would be shown onto your eye, and next moment you have regained your eyesight.
Oh.
It is as easy as that.
Oh.
So it has just done wonder, and it was the first treatment occurred soon after 1960, after the first ruby laser was built.
So it's
Okay, I think now we'll stop it. Already too late. Anybody want to ask question? Last question.
Sir, I want to ask less.
Okay, ask. Okay, ask.
Yeah. Can I ask?
Ask. Yeah.
Sir, actually, the laser is used for this fusion, no, for inertial confinement. I think I read something about it. Can you tell about that, sir?
Yes, actually, you see, if you can deposit huge energy and focus it within a very, very tiny volume, that you can increase the temperature so much that two nuclei which are similar charge, they would repel, but they would gain so much of energy, kinetic energy, that they can actually tear apart the Coulomb repulsion and come close enough to get fused. Because for them to come very close, they should be able to tear the Coulomb repulsion to nuclei. They should approach very, very close. And in order that can happen, you actually impart huge kinetic energy to the two nuclei. That can happen if you can deliver huge energy within a very short time, within a very, very tiny volume. And that can be done with laser because it has very, very small divergence, and you can actually create laser pulse, as I said, of very, very short duration. So that is how you can actually facilitate fusion of two nuclei.
But whether fission or criticality also can be done?
Sorry?
Nuclear fission or even criticality with the help of laser?
Nuclear fission.
Fission not be possible. Fusion.
Fusion, yes. Fusion, but so far, actually the break-even condition, but still research is going on. Break-even condition where you have generated more energy than what you have put in, that has not been achieved so far.
Okay.
Sir, hello, sir. Up to which? I'm Anil actually. Up to which range we can go with laser? Means up to X-ray or further gamma ray, up to high intensity gamma ray?
As the wavelength reduces, the problem that comes is the lifetime of the upper level, excited level. Higher is the frequency, very short lifetime. The level, energy level has very short lifetime. Therefore, maintaining a population inversion becomes very difficult. That is why producing coherent light at shorter and shorter wavelengths is increasingly difficult. Although there are reports of X-ray laser, but yet it has not actually matured good enough to say that we have good lasers available at X-ray region. Lasers, as such, as I said, is available up to vacuum ultraviolet region. But I can't say that we have X-ray laser which are actually commercially available.
Okay, sir.
Okay, I think we'll stop now. It is already 9:30. I think now almost 1 hour 45 minutes. I think I will stop it now. Now it is my present duty to say a word of thanks to Dr. Biswas. When I talked to Dr. Biswas, he was in US. When I sent a mail to him, he immediately told, "I am willing to give the webinar at any time." So he was so prompt. Then we were communicating, and he promptly agreed. And I told him that it would be meant for students. This should be fundamentals. He was readily agreeing for everything. And today's talk was so fantastic. He started from fundamentals. Then he gave all the examples. He had given so many examples that the most important thing for me was aging. How can we go back from time? Very interesting talk. Lot of information about military application. Then his application on conservation of arts. Then archaeology. Then lot of things he has told. So I think he was selling his talk. It's not enough for him to complete his talk in 1 hour. He asked me give one more slot. So I told him we'll give it. Not now, after a month or so. So he'll give the butterfly effect and all. He told me he can explain in the next talk. So we'll make an arrangement now to give another talk. Now, on the behalf of our Atomic Energy Retirees Association of Kerala, I would sincerely record my thanks to Dr. Biswas. Such an excellent talk. I am very happy, and all the students. You can see the attendance today. It was close to 100 for the first time in the history of our webinar. Such a large number of students coming is for the first time. So I am very thankful to him, and I also want to thank all the participants who have taken a lot of pain to come and attend. I would like to record my thanks to Dr. K.L. Joy, Principal of St. Thomas College, Professor Sunil, Professor of St. Thomas College, Professor Joyce from Zoology Department, St. Thomas College, and Mr. Ashwin, MSc Biotechnology student of UC College, who helped me in arranging this YouTube link and all. He was very helpful to me. So I am very happy that we could make such a wonderful talk. And this talk from here onwards, we are concentrating on our talk will be on mainly for students. So we are thinking of fundamentals, and we are expecting more participation from our students. So Dr. Bishwas, thank you very much. Thank you very, very much.
I also
Thanks a
enjoyed
lot.
interacting with students. And,
yeah. So we'll arrange once more. No, what happened? We can arrange once more. After, let it be some 3-4 lecture be over. Then after maybe the end of April or May, we can arrange one more talk.
Okay, we'll be in touch.
We'll be in touch. And one more thing I want to inform you that we are recording this talk. We recorded this, and I will get it edited because there will be so many this thing that audience noise will be there. So I will get it edited. After editing, I will upload in the YouTube, so anybody can watch it.
Can I know the number of participation today?
It was more than 110 was the Zoom. Then many people have participated through YouTube link.
Okay.
That I have to see. Okay. 110 people I saw in Zoom.
Okay.
Then what happened? Zoom will not allow more than some number of people. Though we have to pay more. Although we are paid, see, our limit is only 100 people. If you want 300 or to 500 people, you have to pay more. So we have not done that. So many other people are joined through YouTube. I will inform you how many people are possible in a YouTube link. And we have told students to give feedback.
Okay.
So they'll give feedback, and then I will get you all the feedback.
Okay.
Okay, sir. Thank you very much. Okay. Thank you once more. Thanks for all the participants. Thanks. We'll stop now.
Yes.
Okay. Thank you, sir.
Thank you very much. Thank you. Thanks for coming. Thank you for coming. Thanks.
It was a
Thank
nice
you, sir.
session, sir.
Thank you.
Be grateful if you arrange one presentation on
Thank you, sir.
Heavy water also, sir.
What is it? Heavy water. Okay. Actually, heavy water we already arranged one. Actually, the first webinar was on heavy water. That was given by Dr. Bhaskaran.
Sir, I think many.
He was the chairman. He was the chairman of heavy water board.
Okay, many people joined now only in this large forum.
Okay. We'll arrange once more. We can arrange. No problem. We'll arrange it. Don't worry. Now this will be in every 2 weeks. Every 2 weeks we will be arranging this webinar.
Was that also available on the YouTube? That heavy water board and all?
No, at the time, what happened? It was a free this thing we have done. So free means they won't allow you to record. Now we are paying for this Zoom. Now we can record it.
Sir, always this interactive session will be much more beneficial than the.
Okay. Next time, what happened? We can give more time for it. But Adam, it's already too late now. You will be too tired. 7:45 he came. It's 9:35.
No, sir. In different time.
Yeah, that we can have. No problem. Hope you all of you enjoyed. Thank you very much. Thank you. So I'm going to end it.
Thank you, sir.
Thank you very much. Please do.
Good night. Thank you very much, sir.
Thank you.
Thank you, sir. Good night.
Thank you.
Thank you,
sir. Good night.
Oh, it is very good. Very good.
But unfortunately, what happened? No, നമുക്ക് ആളുകൾ കൂടി. നമ്മുടെ Zoom subscription അത് 100-110 പേര് കൂടെ അയാൾ സ്റ്റോപ്പ് ആക്കും പിന്നെ. So what happened? We cannot. അപ്പൊ അതിന് ഞാൻ യൂട്യൂബിന് ലിങ്ക് അയച്ചു കൊടുത്തത്. യൂട്യൂബിൽ
പിന്നെ ഈ സൂമിന്റെ പുറം ഇന്നലെ ഇതുപോലെ അനിൽ കാക്കോക്കറിന്റെ
100 പേരും കൂടെ അതിന് വേണമെങ്കിൽ അല്ലെ നമുക്ക് 300 പേരെ അടക്കാം. 8,000 rupees per month.
That is too much. We'll see that from the response we can.
അല്ല 8,000 രൂപ.
നമ്പൂതിരി സാർ.
അതെ നമ്പൂതിരി സാറ്. ആരാ?
ഞാൻ കൈകാര്യം എനർജി സ്റ്റേഷനിലാണ്.
ചെറിയാൻ.
ഓ പറയുക.
സാർ ഞാൻ ജോയിൻ ചെയ്തപ്പോ സാറ് ജസ്റ്റ് റിട്ടയർ ചെയ്യാനായിട്ട്.
അതാണ് ഞാൻ ഓർക്കണില്ല കേട്ടോ. സോറി.
സാറിനെ പെട്ടെന്ന് ഞാൻ കണ്ടു. വളരെ ഹാപ്പി. സാർ ഇപ്പൊ എവിടെയാണ്?
ഞാൻ ഇവിടെ